Pictured below is the y versus t graph for a projectile. The reason why it's curved is they're talking about an object just thrown up into the air. So when you do that, the difference between like a rolling bowling ball and a ball that's thrown up into the air is that for this bowling ball, we say that the forces on the ball are actually balanced, where even though gravity pulls the ball down pretty hard toward itself, there's also a force supplied by the floor itself called a normal force. Force is like a push or a pull. And forces are said to be balanced, the blue ones. And so, according to Newton, what should happen is the ball should travel with constant velocity unless acted upon by an unbalanced force. But there's not an unbalanced force for the most part on the rolling ball. That's different from a ball that's like, say, thrown up into the air. So if you have a person grabbing a ball and hurling it upward like this, we know that the thing doesn't travel with constant velocity because it doesn't go all the way to outer space, you know? If it did have constant velocity, it would go to the moon or whatever. But it doesn't do that, of course, because velocity is not constant. He's pulled down by Earth with a force of gravity. It's called an unbalanced force. It causes acceleration of the object to the point where it eventually comes to rest for an instant where the velocity becomes zero, and then the thing starts falling back down, and that's what this graph is supposed to show. Now, because the velocity is changing, you can tell that because the thing is a curve. When you have a curved position versus time graph, then your velocity is changing. So we have acceleration happening here. And they're asking us to document in terms of like meters per second, what is the speed like at different points. So you should find a point on your curve at t equals 0. Here's the t equals 0, and there's the point in question. You could imagine that you are walking up a steep hill at this time. You're there, and let's say that you are trying to get to the top of the hill. This is a grassy hill, so like a profile of Earth. Now, you all feel that like great feeling when you get to the top, right? It's like, wow, I just conquered that hill and I'm feeling pretty good. Why are you feeling pretty good? Where's it easier to walk? The bottom of the hill or the top? The top, right? At the top, walking is easy. And at the bottom, it's not. Okay, so that is related to the steepness of the slope. So where's the slope most steep? At the bottom of the hill or the top? Bottom, right? That's where it's steepest. Top is where it's, you know what the slope is at the top? The slope is actually, I'll say not steep, let's put it that way. Right? So you have to estimate the slope of this curve. That's a difficult task. So let's do this. Find what's called a tangent. So a tangent is when you draw a line that's going in the same direction as the slope. So the black there is my tangent. Now, it has the same angle basically as the hill at the point in question. If I were to move that tangent somewhere else, we would see that the slope, it wouldn't match the hill at all. And if I moved it over here, my slope's going up while the hill slope's going down, so they don't match at all there. But there's one location where that tangent is the right line to draw, and that's right here. Now what you got to do in order to solve this is to find a place where your tangent hits the hatch mark crossings. So like right here, for example. That's a place where you're at the crossing of the hairs of the graph, right? And also right here at your starting point, that would be a good point as well. So these 2 points can be used to estimate the slope of the graph. All right, all you got to do is just make a triangle. Simple as that. Okay, you could shade it in if you want, but you need to know the slope of that triangle. The reason why is the slope of that triangle is going to be the best estimate of the true slope of the graph at the point that you're standing at. So you just need to know the delta x and the delta t for your triangle that you had created. So you could identify the points in question. So like this point here is 3, 9. And this point is, of course, the origin, 0, 0. So our delta x then is going to be 9 minus 0, which is 9 meters. And our delta t here is clearly 3 minus 0, 3 seconds. And so if we're estimating that velocity, we're going to use the formula for average velocity. And you want to do delta x over delta t. That's how you find it. And it's apparently 9 meters over 3 seconds. So it's 3 meters per second. All right, now if they asked about the slope at the top, if you're doing that, you got to have a line that's going at the same direction as the curve. Okay, that's my tangent line. And now you got to get the slope of that line. But what's the slope of that line, really? It's 0. Yep. You could take 2 points if you need to and do a calculation on it. So you got your 10, 18, and you got your 14, 18. So the calculation for this slope is that the slope will be your 18 minus 18 over 14 minus 10, that's 0. So we see that the slope went from 3 meters per second down to 0 meters per second over time. Now it didn't just suddenly jump from 3 to 0, it changed gradually. And so what you should be able to do is create a graph, which is a graph of your velocity versus time. Okay, so what do I mean by that? I mean, it is often helpful, like as an analytical tool, to graph your velocity and your position stacked one on top of the other. So let me just show how I would sketch one here. All right, so try to line up the axes so that the times of each graph coincide, like this. Okay, and then we're going to create a velocity graph. You got to use some facts that you have from the graph above, like some evidence, just like some starting points that are like irrefutable. One that's irrefutable is that the initial velocity of this guy is 3 meters per second. So when you go down below, the value of the velocity versus time graph is the slope of the above position versus time graph. So if the slope here is 3 meters per second, then my initial value of the velocity needs to be 3 meters per second. It's also irrefutable that the velocity at a t of 12 is 0. I just proved it right there. And so when I go down below, I need to make sure that when I trace that maximum value, that peak down, I gotta have a velocity of 0 at that point. And you might be thinking, okay, how does the velocity change from 3 down to 0? Does it just like jump down like this, or does it go like that? Luckily, it's the simplest situation. It's just a straight line. That's it. That's how gravity affects the velocity continuously. And so we would have that. And even if we go one step farther now, we can now talk about a thing called acceleration. Acceleration is how your velocity changes with time. And you need the acceleration versus time. You need the value of the acceleration versus time graph to be the slope of the velocity versus time. Now, what about the velocity versus time graph? Is that thing having a changing slope, or is that a constant slope? Because this sure was a changing slope. I proved that. Yeah, that's a constant slope. So what that means is we have constant acceleration, because the acceleration, his value, is the slope of the velocity. Okay, with that in mind, we can now sketch our acceleration graph. So it can't change the acceleration. It has to be one value that never changes. That means it's horizontal. It's got to be a horizontal graph. Do you think it would be above the axis, at the axis, or below the axis based on the slope that you see above? Above. Interesting. Is that a positive or negative slope? It's called in math a negative slope because it is sloped to the right and down. Okay, that's a negative. Because see how the velocity went from 3 down to 0, and eventually it's going to go to negative 3. The velocity is going negative, so this is an example of negative acceleration. So just a nice horizontal like this. Now for free fall, we know what that value of the acceleration is. It's always a constant. That's something we'll use in our next lab. And what it is the acceleration due to gravity is going to be negative 9.8 meters per second squared all the time for any object that's in free fall.